Okay, and we are back with day 4, scientific notation and roots. So we got a couple of essential questions today, which hints to you that we have two topics that we are going to be exploring. The first is how can I write numbers in scientific notation? Many of you have seen this already. I am just going to show you a different way of thinking about it, somewhat a shorter way. I'll talk about some other things when we go through it and explore the topic as well. And the second question is, how can I simplify square roots? And we'll kind of explore that topic as well. But let's dive right into scientific notation. Let's take a look at example A. If I'm looking at example A, scientific notation has a lot of rules, but the first rule is that I'm going to write the first digit of the number, non-zero digit, and then I'm going to put a decimal and then the other numbers until I just run into zeros. So one digit, the 3, a decimal, and then the other numbers until I hit the zeros. I know this is a really confusing thing, and if this is your first video on scientific notation, I'm taking a lot of shortcuts. So this is just a quick and dirty review. There are better things out there to break down and explain exactly why all of this happens. I am just reviewing. So scientific notation also says that I'm always going to multiply by 10. So I'm going to raise 10 to an exponent. I'm just moving the decimal from the end of the number, all the way to right behind the 3. But really, in order to see that, I'm just going to write the number again, and I'm just going to cross out all of the numbers until I only have the number before the decimal. Kaboom, it's 6 numbers, so the exponent is a 6. Sweet. All right, let's do the same thing for B. If you want, you can pause the video now, and then you can try to do B on your own and then check it. If you didn't pause it, then you're right with me as we go along. It's going to be 6.7 because 6 and 7 are after 7 is I only have zeros. So 6.7 times 10. And then to find the exponent for 10, again, I'm just going to cross out the digits until I only have the first one, non-zero one remaining. Cool. 10 to the third power. I crossed out 3 numbers, 10 to the third power. Just like for A, I crossed out 6 numbers, and then I had the 3, so the exponent is 6. Sweet. So let's take a look at C. If I'm taking a look at C, it's the same deal, 5.23, because I only have one digit, a decimal, and then all of the numbers until I just run into zeros, times 10. And then I count how many numbers I can cross out till I only have that first digit remaining. And that, of course, is 7. Awesome. Now, D, E, and F are definitely different. In fact, they're all decimal numbers. So I'm going to kind of tackle these differently, and I did something originally in my notes, and a student of mine has pointed out something, so props to that student, and I will talk about that as we go. So scientific notation, the first non-zero number, and then the digits after that, so 3.7 times 10. Cool. And now what I'm going to do is this method, I can say I can cross out the numbers until I've crossed out the first one. So I cross out 2 numbers here, and the exponent is -2. Now decimal numbers, these are very small numbers. These are different than before, so that's why I start counting after the decimal. And it's negative because the number is a decimal and it's small. So I'm going to dive into E. And then let's take a look at another way that we could do this. And this is not on the screen, but I can describe it to you. So again, 2.03. 2 is the first non-zero number. And then I have 0.03 because I have to keep going until I finish the number here, or I've already gone past all of the zeros for the decimal numbers here. And then I'm going to cross out numbers until I've crossed out the first. A student actually pointed out to me that, hey, you got 4 zeros in front, so it's -4. Here I have 2 zeros in front, so it's -2. Both of these ways work, and in fact, if you're looking ahead to the next problem, I've got 5 zeros in front, so it's -5. Alternatively, you can do the method that I have here on the video, which is cross out numbers after the first decimal until I get to the first non-zero number and cross it out. That gets me the same exponent, which is -5. Now, the super important is to realize that very big numbers, like we saw on the previous slide, and very small numbers, like we see on this side, are different. That's because the small numbers have a negative exponent, and the larger numbers have a positive exponent. So that's the big difference. So we're going to keep on going, and there's a couple of things that I'd like you to notice. In scientific notation, how many numbers are in front of the decimal? If you said 1, you are correct. And then when the exponent is positive, what kind of number is it in standard form? Of course, that number is large because the exponent is positive. And when the exponent is negative, what kind of number is it in standard form? Well, in standard form, that number is, and if you said small, you're also correct. So that kind of wraps up the quick review on scientific notation, and let's dive into square roots of numbers. So really, square roots of numbers in words is a number times itself that equals the root. Let's not worry about symbols, and I think it's easier to see in practice. So all of these examples lead to different types of discussions. The first one here, 9 over 16. So really what that simplifies to is I'm taking the square root of the numerator and the square root of the denominator. So 3 times 3 is 9, and 4 times 4 is 16. Sweet. Now h is different. It's got this funky symbol in front. That's a plus minus symbol, or plus or minus. And then I have a decimal, 0.81. All right, so the deal is I know 9 times 9 is 81, but I have 2 decimal places. Half of 2 is 1, so my answer must have 1 decimal place. If I had 0.0081, then this would be 0.09. The answer would have half the number of decimal places as the root. Awesome. Now for I, it has a negative in front, but I know the square root of 49 is 7. 7 times 7 is 49, and the negative just stays. Cool, negative 7. Many of you are looking at J and thought, oh, negative 10. But can you multiply the same number and get a negative answer? Well, negative 2 times negative 2 is positive 4, and in fact, negative 10 times negative 10 is positive 100, and any negative times itself is going to give us a positive number and not a negative one, so no. Which means that our answer is undefined, or really, it's a non-real number, which is the best answer. Some tests and some people might say undefined, but hey, non-real is the best answer here for J. And K is just kind of an extension of I. We already know what this is. It's negative 4 over 7. 4 times 4 is 16. 7 times 7 is 49. Many of you have already probably skipped ahead to L, and you know it's 12 over 5. And if you knew that 13 times 13 was 169, then kaboom, negative 3 over 13. Now, n is different. N is very different. I'm going to first look at just simplifying the fraction on the inside. So really, 196 over 72, I'm going to divide it by 4, and that gets me 49 over 18, which is kind of like what we saw here in G. I'm taking the square root of 49 and the square root of 18. I know that it's 7 times 7 is 49, but no number times itself is 18. And mathematicians really hate having a denominator that has a radical symbol or a square root symbol. So I'm going to do what's called rationalizing the denominator. Yeah, that's right, rationalizing the denominator. Sounds scary, but all it means is multiply this answer by the square root of the denominator twice. One in the numerator, one in the denominator. What this does is it doesn't change the value of my answer at all, because of course the black part here would reduce to 1. But it does remove the square root in the denominator. I'm going to call this done because for the purposes of 8th grade math, I've already extended past what your textbook has asked me to do. If you're looking at this video and you're like, wait, I know that the square root of 18 is 9 times 2, and 9 is a perfect square, and so it's just 7 times 3. And yeah, it's 21 or square root of 2 over 18. But we're not concerned with that in 8th grade, so this is perfectly fine. In fact, if you just get to 7 over the square root of 18, then you're already beyond what the textbook is asking. Okay, cool. And that's square roots, ladies and gentlemen. What number times itself is equal to the root? And really, that just takes us to the end of our discussion here. If you're in my class, write your summary, make sure your table of contents is updated, and if you want to challenge, pause the video, take a look. I'm not going to show the answers, but a lot of these real-life application questions kind of connect back to this exploration of scientific notation and of square roots.